Okay, the end of chapter one deals with sort of a review of general chemistry in terms of acids and base theory. Now, there's actually quite a bit of difference between the way we look at acids and bases in general chemistry and the way that we look at acids and bases in organic. And so, what I'm going to do is kind of just review what you learned in general chemistry about acids and bases, and then we'll expand on that here into organic, what's important, and even more so on Friday in class. So there's basically two primary theories of acids and bases that you start with in general chemistry: the idea of the Arrhenius theory, and then the Bronsted-Lowry theory, which was sort of co-discovered or co-coined by Bronsted and Lowry independently of each other. Now, the Arrhenius theory of acids and bases simply described acids and bases in terms of their chemical properties, and if also in some cases physical properties. So Arrhenius said acids did things like dissolved metals. They changed the colors of certain plant pigments like litmus to red, and they had sort of a sour taste. And we might think, well, nobody's tasting hydrochloric acid or nitric acid, nor should they. But if you think about things like citric acid or vinegar, which are acids, they do have a distinctive taste. In terms of bases, Arrhenius proposed the idea that they changed certain plant pigments, in one case litmus to blue, and that they had a soapy feel and sort of a soapy taste. And so if you think soaps are actually bases, and so they do have a slippery, soapy feel. Now, Bronsted and Lowry redefined, or they used a stronger definition or a more precise definition of acids and bases. And so, in the Arrhenius definition, he just simply proposed that an acid or a base was something that an acid produced H+, which we now know combines with H2O+ to form H3O+, when you dissolved in water, and a base produced OH-. And so that was the basic definition that Arrhenius used. So we know that things like HCl, if you dissolve them in water, you get H3O+ or H+ and Cl-. Sodium hydroxide you dissolve in water and it produces hydroxide ion. And ammonia would also be an example where when you react ammonia with water, you also get NH4+, and you get the OH- there, so ammonia would be considered a base under the Arrhenius definition. Bronsted and Lowry kind of made this a little bit more general in terms of their definition, and they proposed the alternative definition that we're going to define acids and bases based on what donates something and what accepts something. And in the Bronsted-Lowry acid-base theory, we have these things donating protons and accepting protons. And so that same example of ammonia reacting with water, we know that the water will donate a proton to ammonia to make the ammonium ion, and losing the H+ will then give you hydroxide. And so in this case, we would say that the thing accepting the proton, of course, is the base, water is the acid, and so in the forward reaction we would get the ammonium and the hydroxide. And so that's a definition that we used in general chemistry for most of the acid-base stuff that you did. Now, the acid-base theories in general chemistry, if you remember, you had to draw ice charts and you had to calculate pKa's or calculate pHs of solutions. We're not going to do that in organic, and I'll kind of explain why. It's difficult to do quantitative work in organic chemistry with acid-base theory, and I won't get into all the nitty-gritty details, but there are some limitations on what we can do. So we're going to take a much more qualitative approach to acid-base chemistry and organic. When you talked about acid-base in general chemistry, you talked about conjugate acid-base pairs. And so your conjugate acid-base pairs were basically the sort of base after an acid reacts that's produced, or when a base reacts, what acid does it produce? And so one of the things that when I teach general chemistry I like to talk about is the idea that when you're talking about conjugate acid base and you say, what's the conjugate acid? We really should think about that as, what is the conjugate acid of the base? So if you say it that way, then you know that the base is picking up a proton to become an acid. Or what is the conjugate base of the acid? So when the acid loses a proton, what base does it become? And if you remember, the reason why we have to know about conjugate acid-base pairs is that in an acid-base reaction, the acid becomes a base on the other side of the equation and vice versa. So if we look at these examples, could we figure out what the conjugate acid or base is? So if I take ammonia, what's its conjugate acid of the base ammonia? So its conjugate acid would be NH4 plus. That would be its conjugate acid because that's the acid that produces ammonia. Now, we don't in general chemistry think about what the conjugate base of the acid ammonia would be, because ammonia doesn't lose a proton in water. But if I wanted to know what the conjugate base of ammonia would be, it would be NH2 minus. So if ammonia loses a proton, it produces NH2 minus, and we'll actually use this base later on in the semester. So it's a legitimate base. It's a very strong one at that. Cl minus can't act as an acid because there's no H plus. So we would say, what is the conjugate acid of Cl minus? And its conjugate acid would be HCl. Sulfuric acid cannot accept another proton, so it would be an acid. What's its conjugate base? HSO4 minus. And what's the conjugate base of HSO4 minus? SO4 2 minus. Water, conjugate acid of the base water would be H3O plus. Its conjugate base would be hydroxide. What's the conjugate base of hydroxide? An oxide ion. And hydroxide, its conjugate acid would be water, and its conjugate base would be oxide. Okay. So we have to be able to identify conjugate acid-base pairs. This is going to come into play when we write equilibria for acid bases, and if you also remember that there's a relationship between acid and base strength between the conjugate acid and its conjugate base and vice versa. Now in general chemistry, everything is based on aqueous solutions, and everything is based on a pH scale of 14. And do you remember where that comes from? Well, if you have water, or actually if you have any solvent, and let's just say I've got H solve for a solvent that has a proton. Well, when we react two water molecules together, we can get the autoionization equilibrium where one water donates a proton to the other water, producing H3O plus and OH minus. More generically, this autoionization can actually exist in any solvent that has a proton. So you could write a sort of an auto-ionization equilibrium for any solvent, including some organic solvents, where you would have the solvent molecules being in equilibrium with their ionized forms. And the big problem when we move from what we talk about acid-base chemistry and general chemistry up to organic is that we're no longer using water as a solvent, because most organic molecules don't dissolve in water because they only have dispersion forces. And so if we're going to make pH-like measurements for organic molecules, we can't do it in water, and we've got to use another solvent. And so this equilibrium becomes different for that solvent, and so do the mathematics of what its equilibrium constant Kc or what its equilibrium constant Kw is. In general chemistry, we know that Kw is simply equal to this expression, and in pure water that's been determined experimentally to equal 10 to the minus 14th, and so that's where our pH scale of 14 comes from. If we were to move this to another solvent, we might end up with a pH scale that would be not 14 at its maximum, but it could be as high as 45 or 60, depending on what this auto-ionization equilibrium is, and a lot of times if it even can be measured, because it's usually very, very, very small. So our pH scale comes from the fact that if we solve for this equilibrium of 10 to the minus 14th, the H3O plus OH minus concentrations in pure water is each 10 to the minus 7th, and therefore that's where our pH, a neutral pH of 7, comes from. Anything lower than that means the H3O plus is greater than OH minus concentration. Anything higher than a pH of 7 gives the OH minus higher than H3O plus. And so we have this pH, POH, where we can take minus the log of hydronium or minus the log of hydroxide ions and get our pH or our POH. When we change to an acid, then we have an equilibrium between the acid protonating the water to form H3O plus and the A minus, and so that, depending on the strength of this acid, that equilibrium constant, which we would typically call Kc, but in this case it's Ka to stand for this particular acid equilibrium expression, that's going to equal the hydronium times the A minus concentration over HA. Remember that for equilibrium constants, pure liquids and pure solids don't show up in the expression. Now, if I look at this equilibrium, what's the relationship between HA and A minus? They're conjugate acid-base pairs. What's the relationship between water and H3O plus? It's a conjugate acid-base pair. And if we look at this equilibrium from that standpoint, we have the conjugate acid becoming the conjugate base, and the conjugate base then becoming the conjugate acid. So that if I reverse the equilibrium, H3O plus would be the acid, A minus would be the base, to then reverse the equilibrium to form HA in water. So these equilibrium constants then, in general chemistry for the most part, for most of the acids that you used were very small. And so instead of talking about the Ka of an acid, we would talk about its, I guess I didn't put this expression in, we would talk about its pKa. So the pKa is equal to minus the log of the acidity constant. Now, what happens if we have something that has a pKa of 5 versus something that has a pKa of 10? Which of these two compounds, if compound A has a pKa of 5 and compound B has a pKa of 10, which one's the stronger acid? Well, this would be a Ka of 10 to the minus 5th. This would be a Ka of 10 to the minus 10th. And so 10 to the minus 5th is a larger number than 10 to the minus 10th. So remember that when we have pKa, the the lower the pKa, the stronger the acid. And I like to remember that by saying, remember that the more acidic solution is the one with the lower pH. It's the same concept. Now, there's all sorts of tables that involve relative strengths of acids and bases. And this just happens to be, one of them that we can use. This is a non-mathematical chart, so there's no Kas or no pKas for this chart. It just simply relates the strength of different acids and their conjugate bases. Okay. Now, let me go to a blank slide here. We have to define two things: strong and weak. In acid-base chemistry, what does it mean to be a strong acid or, conversely, a strong base? It means that you have complete dissociation in water. Classic example of a strong acid is HCl, because when I react HCl with water, I get 100% of H3O plus and 100% of Cl minus. Okay. And maybe later on I'll say that that's not totally true, that it's 100%, but this is what we call complete dissociation. So complete dissociation in water means something is strong acid, or if it's a base that completely dissociates into its ionic forms, then it is a strong base. And NaOH would be an example of a strong base. By definition, or by contrast, what does it mean to be a weak acid? Well, if you said that a weak acid was only partial dissociation in water, you'd be right. And how do we represent that an acid only partially dissociates in water? Well, from general chemistry, the classic example is HF. When HF reacts with water, what happens? We get an equilibrium between the H3O plus and the F minus, the conjugate base. And so we define by definition the partial dissociation in water to be a characteristic of a weak acid or a weak base. If you remember back to general chemistry, anytime you did an ice chart, you were always doing an equilibrium problem that involved a weak acid or a weak base. Strong acids and strong bases, if I said, well, I have a 0.001 molar solution of HCl, I know that since it completely dissociates, I'm going to end up with 0.001 moles of H3O plus. So we have to have this, we have to make sure that we remember the definition of strong is complete dissociation, weak is only partial dissociation. Now you may ask yourself, what would it be if there was no dissociation of water? What if I took something like chloride and I tried to react it with water to form HCl and, in this case, hydroxide? Would that reaction work? No. There'd be no equilibrium. It would be 100% of Cl minus and water. In other words, we get no dissociation, or we get no reaction of something and water to form H plus or hydroxide. So in this case, I have to make up my own definition, and so what I call things that are non-acids or bases is that there's basically no reaction with water. So chloride's an example of something that won't react with water, because if I dump sodium chloride into water, it's not like I'm magically going to make HCl, right? If I'm cooking spaghetti and I throw sodium chloride into the water to make, or to basically flavor the water, not to give it an increased boiling point and make it cook faster. That's not true. But if I throw sodium chloride in water, I don't have to worry about my pH of my solution being like 2 and the solution really acidic, because I'm not forming any HCl. So I classify acids and bases as being strong, weak, and non. And so if we go back to our chart of acids, of just acids and bases, on this chart, things like perchloric acid is at the top, so this is the strongest. So over here, this is the strongest of acids. And then down here, I've got the weakest, and I may cross this out and say that down at the bottom of the chart is a non-acid. But this table then, as you go up this table, you've got increasing acid strength. So things like perchlorate, perchloric acid, sulfuric acid, HCl, nitric acid, and the hydronium ion itself, H3O+, those we classify as strong acids, and we say that those completely dissociate in water when we add them to that. So we get complete dissociation. So these are our strong acids. Now what is HSO4, phosphoric acid, all of these down through, in essence, water. What's this group of acids going, how are they going to be classified? Well, if you remember back to general chemistry and you did ice charts and all of those, we used ammonia a lot of times, you used HCN, you used acetic acid, which is up here, which is vinegar. H3PO4 is classified as a weak acid. HF isn't on this chart, but HF would be in here. So this group is our weak acids, which means that it does what? Partially dissociates in water, and so we get an equilibrium. Now what are these guys down here? Well, things like, this is alcohol, ethanol, things like ammonia, H2, CH4, these things do not react with water, and so these are going to be non-acids. So they don't react with water. Even though I wrote the conjugate base of NH2- as its conjugate base, that's true, it is of ammonia, but ammonia will not react with water. It reacts as a base, not an acid. And so ammonia won't give up a proton to water. So strong acids, weak acids, and what I consider to be non-acids, which means they just don't react with water. So now I come over here to the conjugate base side. Perchlorate ion is the conjugate base of perchloric acid. Chloride is the conjugate base of HCl. Nitrate's the conjugate base of nitric acid. So I can draw my same lines here. And now I can ask the question, well, how would I classify this set of conjugate bases? What are they? If you said non-bases, you're right. How about this group? How about them being weak bases? Because they're going to be in equilibrium with their conjugate acids. And then down here, how about these guys as bases? What are they? Well, they turn out to be the strong bases because they would completely dissociate in water. If I took NH2- and I dropped it into water, it's going to completely deprotonate the water to form 100% hydroxide. If I put H- in water, it's going to completely dissociate, or it's going to completely react with water to form H2 and hydroxide. So what I have is relationships that don't make sense in English definitions. The opposite of weak is weak. The opposite of strong is a non-acid or a non-base. Okay, and if I was introducing this in class, I might ask, what's the opposite of strong? And I can always get a couple of people to go weak. Yes, in English that's true, but not in chemistry, and not with acids and bases. Okay? So what happens is that if an acid completely dissociates in water, then its conjugate base isn't going to react with water. And vice versa down here with the strong bases. If it completely reacts with water, its conjugate acid isn't going to give up a proton to water or deprotonate water. So that's how we classify acids and bases. I guess that's kind of my definition, is that we just have to remember weak acids give weak bases, strong acids give bases that aren't bases, and strong bases give acids that aren't acids. But all of this is in water. And once I change the solvent, I can change how strong or weak an acid or base can be. Here's another question I like to ask. I like to ask the question that what is the strongest base that can exist in water? Okay. Well, I was going to say hold on to that answer until Friday, but the strongest base that can exist in water is hydroxide. What's hydroxide? The conjugate base of water. So if I broaden this question out and I said, what's the strongest base that can exist in a solvent, you would say the base of that solvent, the solvent's conjugate base. And since the solvent's conjugate base might change in strength, when we change from water to other solvents, we change the numerical aspects of pKa. And so our pH scale of 14 would not be relevant for water. And so measuring the exact pHs or pKa's of organic acids that don't dissolve in water means that we'd have to use another solvent. And as soon as I change that solvent, I'm going to change the pH scale, and I'm going to change how that acid or base reacts. So in general chemistry, everything's nice because we work in water. In organic, not so much. But these basic principles still exist. Strong acids give non-bases. Weak acids give weak bases. Non-bases have strong, or non-acids have strong bases as their conjugates. You might say, who cares? You can say that about a lot of things. But when we look at an equilibrium reaction and we want to know what side the equilibrium lies to, I need to relate the acid on the reactant side with the acid on the product side. And I need to compare the base on the reactant side with the base on the product side. And so if I want to know, for instance, where the equilibrium lies for HCl plus H2O, the first thing you should say is, but you just told us there's no equilibrium. And you're right. There isn't an equilibrium. But let's just imagine there was. I would look at the strength of HCl versus the strength of H3O plus. I'd go back to my chart here and I'd see that HCl is a stronger acid than H3O plus. Therefore, the equilibrium would be pushed to the weaker side. Can I do it with bases? Absolutely. What's a stronger base? Water or chloride? Go back to my chart. Water, where is it? As a base, water is a stronger base than chloride. So, actually, should H3O plus be a strong acid, or should it be classified as weak? Yeah, you know what, it probably should be classified as weak. So anyway, water is a stronger base than chloride. So coming over here, that's the stronger base. So notice the stronger acid and the stronger base are on one side, the weaker acid and the weaker base are on the other side. The equilibrium lies to the product side. And again, in this case, there's no equilibrium because I've classified HCl as being a strong acid that completely dissociates. All right, here's an example. Can we predict the products of this reaction and then predict what side the equilibrium lies to? Well, so I'm going to take HPO4 2 minus, and I'm going to react it with HCN. With HCN. And I'm going to get an equilibrium. So what are the products of this reaction? Well, this is an acid-base reaction, so something's got to act as the acid and something's got to act as the base. Well, if I just look at this, HPO4 2 minus could act as either the acid or the base, right? It could either pick up a proton to form H2PO4 1 minus, or it could lose this proton to form PO4 3 minus. So this could be either an acid or a base. Now looking at HCN, can HCN pick up a proton? Well, if you drew out the Lewis dot structure of HCN, yeah, I suppose there's a lone pair on this nitrogen that could pick up a proton. But I'm getting ahead of myself and talking about Lewis acid-base chemistry. H2CN plus doesn't exist. And so HCN can only act as an acid. And so if I say that HCN is going to act as an acid, my product is going to be H2PO4 minus 1 and CN minus as the other product. Where does the equilibrium lie? If you want, take a minute, stop the tape, and see, can you predict which side the equilibrium lies to? Now, do I have that chart memorized? Yeah, no. Let's go back. What was I comparing? Oh, now I got to go back this way. Let's label acids and bases on either side. Well, we just did this. HCN is the acid, and now HPO4 minus is the base. So this is the base. What happened? HPO4 2 minus picked up a proton, so its conjugate acid-base pair is here. What happened with HCN minus? HCN minus became the base CN minus, so there's its acid-base conjugate pair. So now let's compare acids. Which of these two acids is stronger? HCN or H2PO4 minus? So now I go back to my chart. I see HCN down here. Here's HCN. What was I looking for? H2PO4 minus was the other acid. Which one's the stronger acid? H2PO4 minus. So this one is the stronger acid. Which one's the stronger base? CN minus or HPO4 2 minus? If I had to take a guess, I would say that CN minus is the stronger base. Am I right? CN minus is here. HPO4 2 minus is there. This is a stronger base because remember base strength is increasing as we go down. So CN minus is the stronger base. And the thing is, you'll always have the stronger acid base on one side. If it didn't work out that way, I'd have no idea to predict equilibrium, because what do I consider, the stronger acid or the stronger base? So they're always on the same side. That means the equilibrium here would be pushed this way, so the equilibrium would lie in this case in the case of the reactants. So I'd have more HCN than Cn minus, and more HPO42 minus than this. Okay? And we're not going to get into the mathematics of figuring out what that equilibrium constant is. We're just going to do it in a qualitative sense. Okay? So we have to have some way of understanding acid-base strength, and so we use this type of a chart. If I'm teaching general chemistry, I give the students that chart, and so they have to know how to use it as opposed to memorizing things. Now, in organic, we're going to have a little bit of a difference. So in general chemistry, you also talk about the strengths of bases, and you can have a Kb equation, which would lead you to a POH, and we're not going to be too concerned about that in organic. So here's just another chart that kind of shows you increasing acid strength versus increasing base strength. And you might say that HI, HBr, and HCl, sulfuric and nitric, these 5 bases are what we consider to be strong acids. Now, if you're really, really particular about this, you may say, how can I know that HI is a stronger acid than HNO3 if they both, quote unquote, completely dissociate in water? And the thing is, they don't completely dissociate in water. They just dissociate to give huge Ka values. But they're still measurable Ka values, or even if they're not measurable, there's ways to determine which Ka value is larger. So while it turns out that we treat these as if they're strong and they completely dissociate, there is a way to tell the difference between HI, HBr, HCl, sulfuric, and nitric in their dissociations. And so we do have HI being measured experimentally to be a stronger acid than HBr, than HCl on down the line. Okay, and so it's sometimes difficult when you say, but I can't know that. People have measured that. So our acid-base sort of chemistry, or our acid-base table, is going to come from the periodic table, which is great because we'll always have a periodic table. And it turns out that as we go across the periodic table, and we're just looking at the main group elements here that are important for organic, that as we go from left to right on the periodic table, we have increasing acid strength. So HF is a stronger acid than CH4. Water is a stronger acid than NH3 minus. Remember, NH3 minus to be an acid would have to protonate water and become NH2 minus. Not going to happen. So when we go across the periodic table from left to right, acid strength increases. And I just point out that HF is considered to be a weak acid because it partially dissociates in water, but it partially dissociates in more than water partially dissociates in water, and infinitely more than NH2 minus or CH4 or NH3 and CH4. So general trend going across the periodic table from left to right, increasing acidity. On the periodic table going down, you have increasing acid strength. And so HI is more acidic than HF. Now HF is a weak acid, HCl, HBr, and HI are strong acids, so there's a clear demarcation between HF and these three, but HI turns out to be a stronger acid than HBr and HCl if you try and measure those equilibrium constants, which is difficult to do, but it can be done. So this is our periodic table and trends. So we're going to have increasing acid strength going from right to left, or going from left to right, and then increasing acid strength going from top to bottom. Now what we'll do in the lecture part is this box is going to basically be the core that we're going to use in organic for predicting acid strength of organic molecules. And so I'm going to talk about, so what's CH3 minus as a base? Is it stronger or weaker than NH2 minus? Is that stronger or weaker than hydroxide? Is that stronger or weaker than fluoride? And so we'll come back to this chart, and if you want, you can probably take a guess at these answers, but we'll talk about that in lecture on Friday. So the periodic table is going to be the key. Now, in organic, we use a combination of Bronsted-Lowry acid base to talk about donating protons. But we also use the Lewis acid base definition that was proposed by G.N. Lewis. And Lewis, I guess, really broadened the definition of acids and bases to involve the transfer of electrons. And so whereas Bronsted-Lowry talks about transfer of protons, Lewis says transfer of electrons. And of course, the definitions of acids and bases are completely opposite of that Bronsted-Lowry acid base, where an acid is something that accepts the protons, whereas in Bronsted-Lowry, the acid donated the proton. We're changing what we're donating here to electrons, and then the base donates the pair of electrons. And so this is the basis for your Lewis acid-base definitions. In organic, we don't actually call things Lewis acids and bases. Traditionally, there's been another name for those, and I'll get to that in a moment. So there's G.N. Lewis. The broadening out of this Lewis acid-base definition means that we can talk about sort of reactions of species that really don't accept protons. Things like if you take a metal ion and you place it in water, what's happening to that metal ion? Well, it's being solvated by the water molecule. And if you think about the water molecule having its lone pairs of electrons, the basically water molecule is kind of donating its lone pairs to the metal in order to form this to form a metal dipole or an ion dipole like force. Is it a bond? Yeah, we won't get into that right at the moment. But that's the idea. So we can now talk about taking things that even go beyond just simple protons and organic molecules. Here's an example of a Lewis acid base. If I take BF3 and I react it with ammonia, here are my two Lewis dot structures for these two molecules. Now, boron is an exception to the octet rule because it's a group 3 element, which means it can share 6 electrons, and it's perfectly happy to do that. Although it'd probably be happier if it could somehow complete the octet. But it can't complete the octet by itself because it only came with 3 valence electrons, so most it can share is 6. So what happens is that if you react BF3, or a boron, and this is also true for aluminum, that if you react one of these atoms that is okay with or doesn't violate, but it's an exception to the octet rule that only shares 6 electrons. It could certainly share 8, but it needs something to give it both electrons. And so if we took ammonia and reacted it with BF3, the nitrogen would donate its pair of electrons to the boron to form its single bond, and then the boron would have a completed octet and nitrogen would still have a completed octet. Now, what would the formal charge on this boron be, and what would the formal charge on the nitrogen atom be? Well, for boron, it came with owning 3 electrons. It now owns 1, 2, 3, 4. So the boron would have a -1 formal charge. And what do you think the nitrogen would have? It now only owns 4 electrons. It came with 5. and so it has a +1 charge. Notice that the nitrogen donated its pair of electrons to the boron, but the way we calculate formal charges, if these two split up, they would each get half the electrons, so the nitrogen would lose one and the boron would gain one. So this is an example of a Lewis acid base reaction, and I'll talk a little bit more in class about this arrow, because we use arrows to show the direction of donation of electrons in Lewis acid base reactions, but also this arrow shows the movement of electrons in chemical reactions, and so this is called an arrow formalism. But one of the things that you have to realize early on is that the movement of electrons in this arrow is, the arrow shows the movement of the electrons. So that means the electrons are moving from the tail to the head. And so you don't want to reverse that arrow. So this is an example of a Lewis acid base reaction. Another example that I oftentimes use is in the lab class, we're going to actually isolate different chlorophyll pigments from spinach in week 6, in experiment 6. And what gives chlorophyll its green color is this head group here, which is called a porphyrin group. And inside of this is a magnesium metal that's actually involved in sort of those donations of electrons from nitrogen atoms to the magnesium, and so the magnesium metal gets caught up in this porphyrin group. It gets held in that porphyrin group by, in essence, a Lewis acid, the result of a Lewis acid base reaction. If you took the magnesium metal out of the porphyrin group, the chlorophyll wouldn't be green anymore, like leaves or like spinach. It would actually become a gray color, and the removal of the magnesium is actually an issue when you're trying to put green vegetables into cans, which some people may say you should never do, but if you do this, you have an issue that over time, if the food becomes acidic, the magnesium will be removed from the porphyrin group, and it'll change from being a green color to being a gray color. And who wants to eat gray spinach? Who wants to eat spinach anyway, but gray spinach isn't all that appetizing. It just as an aside, one of the things that they did back in the early 1900s was to replace the copper, or replace the magnesium with copper, and that gave it a really super green color, but it was a tad toxic. So back in 1900s in England, they outlawed the use of copper to sort of make green vegetables greener in color because that was a tad bit toxic. So in organic chemistry, what we do is we don't use the terms Lewis acid base. Traditionally, the terms that we use for a Lewis acid, which remember is something that accepts a pair of electrons, and our Lewis base, which is something that donates the electrons, we use two different terms for these. And it would be nice if we just stuck to Lewis acid base, but traditionally organic chemists don't change very much, and these terms have been around forever. Things that accept electrons then are things that are what we call electron poor, hence their need to accept more electrons. And these electron poor things are called electrophiles. And literally that means negative loving. So an electrophile wants to accept electrons from something that is willing to donate the electrons, which means it's electron rich, and the electron rich species are called nucleophiles. And so we use electrophile and nucleophile terminology in organic instead of Lewis acid base chemistry. So what will happen is in a Lewis acid base reaction in organic, we'll talk about the electrophile accepting a pair of electrons from the nucleophile, the electron rich giving to the electron poor. And my standard comment on this is that in the chemistry world, the rich always give to the poor, and the richest always give to the poorest. And you can draw your own conclusions as to whether in the chemistry world things are different than in other worlds, and we'll leave it at that. So what we'll do in lecture then is we'll go over this. If something didn't quite make sense, certainly that's the second thing after the online quiz, which you'll fill out after watching this lecture. But if you have any questions, ask those. But what we'll do is we'll talk specifically about how acid-base chemistry relates to organic chemistry and some of the organic acids that acid-base pairs that we're going to commonly see, that, and then talk a little bit more about the electrophile nucleophile terminology, and also this idea of the arrows and which way they go in terms of electrophiles and nucleophiles reacting together. Okay, so for Friday there'll be an online quiz to fill out. It'll be the first one. Our quiz in class will be over resonance structures from Wednesday's class. And again, there'll be a homework set for acid-base chemistry and electrophiles and nucleophiles that will be placed on the web after Friday's class for you to practice with more practice problems.